Questions over either of the homework assignments so far? So what we're looking at today is, well, we're still looking at complex numbers. But what we're looking at today is going to be somewhat of graphing complex numbers as well as adding, subtracting. Nothing too overly complicated. Now we do have the complex plane, and that's what's shown here. Now the complex plane is contained two parts. One is the real part, and the other is the imaginary. And for us, if we think of this in the xy coordinate plane, the x-axis is the real numbers and the y-axis is the imaginary numbers. So if we wanted to plot 3 plus I, well, the real part is 3. The imaginary part is 1i, so we go over 3 up 1. Or negative 2 minus I. The real part is negative 2. The imaginary part is negative 1i. And we get this here. Some say that this is our A and this is our BI, where we plot the A and B parts for this here. Now the absolute value of a complex number A plus BI is defined as the distance between the origin 0, 0 and the point AB. Definition of an absolute value of a complex number. The absolute value of a complex number Z equals A plus BI is absolute value of A plus BI is equal to the square root of A squared plus B squared. Because really all we're saying, absolute value of a complex number is the distance from the origin to this point. And if we take the distance formula over and up, well, this distance 3, this is 1 because we're looking at least here in the form of a triangle. Pythagorean theorem, A squared plus B squared equals C squared. Square root. That's all they're getting. That's where this is coming from. And that's how we get that the absolute value of A plus BI is equal to the square root of A squared plus B squared. When the complex number A plus BI is a real number, that is, B is 0, then the definition agrees with that given for the absolute value of a real number, A plus 0i is equal to A squared plus 0 squared is equal to the absolute value of A. That's all. I mean, even if we took this a step further, all we're saying is the square root of A squared. Squared and square would cancel. But if A is a negative number, we take the absolute value of it because it's going to be positive no matter what it is. Questions on this here? Plot negative 2 plus 5i and find its absolute value. Well, if we're going to plot this, we do have a graph here. So the x value for negative 2 plus 5i is negative 2. Our y value is 5. So we go over to negative 2 and up 5. And this is our point, negative 2 plus 5i, or we can say negative 2, 5 in the complex plane. Any questions on how we plotted this here? Absolute value of this complex number is just the square root of A squared plus B squared. A in our case is negative 2. B is 5. Now at this point here, we could plug this entire thing into the calculator and let it do it for us. I would very much, if we are going to plug it in, I would plug it into the 30xs instead of the 84 because the 30xs will simplify it in radical form. It will not go straight to a decimal. Because if we did this by hand, negative 2 squared is 4, 5 squared is 25, and 4 plus 25 is 29. 29, square root of 29 is as simplified as this gets. mainly because 29, I believe, is a prime number. 2 doesn't go into it, 3 does not. 4 does not, because 4 and 7 is 28, it's too close to it. 5 does not, because that'd be 5 and 6 is 30. So that's it. I mean, there's no other numbers besides 1 and 29. Questions on this here? We feel good with this. Plot 3 minus 4i and its absolute value. Well, if we think of this as a point, it'd be 3 and negative 4. So we'd go over to 3, down to negative 4. And this would be our point 3 minus 4i, or we can think of it as 3 negative 4. Be good with plotting the point. Now, if we take the absolute value of it, square root of 3 squared plus negative 4 squared, this time I'm going to show you how to do this in the calculator. Clear that out. Because we can say second square root of parentheses 3 squared plus negative 4 squared is 5. Now this makes sense that it would just come out to be 5, because if we think of this as a triangle, you don't have to write this additional piece in. This distance is 3. This distance is 4. 3 and 4 are the legs of the right triangle, so therefore it has to be 5, because it is Pythagorean triple. Questions on this here? Find 1 plus 3i plus 2 plus I in the complex plane. Okay, now this is something, unfortunately, we were not able to get to how this, or the reasoning why this works, or what they're trying to do here. Because unfortunately this year we had to cut a lot out throughout the semester because of just missed days and this, that, and the other. Now, what we're using for this to find it in the complex plane is vectors. Vectors are what we're going to use. So I'm going to show you how to do this with vectors and then just how to straight add them. Because unfortunately we didn't get to the section on vectors. That was chapter 3, which we ended up having to just skip completely to get to this chapter. But vectors, I believe both of y'all are familiar with, especially if you've ever watched the movie Despicable Me, the first one. Because Gru's enemy in the first one was Vector, yes. And in the movie, he makes the comment that he's committing evil with both direction and magnitude. That's actually what the definition of what a vector is. It's a line that has a direction and magnitude. Magnitude is just the length of the line, and direction, it has a, well, direction. And for any vector, the starting point of a vector, unless stated otherwise, is the origin, is 0, 0. So if we look at 1 plus 3i, and I graphed it, we would go over 1 and up 3. Now, using the fact that this is a smartboard and I can do this, the vector starts at the origin and goes to that point. Oh, we'll need this first. So that right there would be the vector. Now, our other point is 2 plus I. So over 2, up 1. This again, we'll make this next one red. And its vector starts at the origin and goes to this point here. Sure, why not? Let's make them all. Infinite clone. Okay. So we're good with this so far, yes? Now when we add 2 vectors together, we go tail to head, or tail to point. So tail is where it started, point is where it finishes. So what we can say, if I'm adding these two together, is I can take this vector here and put its tail on the point of the other. Or we can do it the other way. I can take the other vector and do this here, tail to point. So when we're adding two vectors together, we go tail to point on both. And the resulting vector, we'll call it this color, is from where the two tails or two points connect. So where the two started, where they connected together at the origin, to where the 2 points are in the end. And if we look at this here, the point where they stop, this point up here, is at 3, 4, which as a complex number is 3 plus 4i. Now, if we're subtracting, we go point to point and tail to tail. So one of them ends up flipping. And we'll see that here in a minute. So really, when we say 1 plus 3i plus 2 plus I, we get 3 plus 4i. If we're doing this in the complex plane, we were graphing this. If we did this algebraically, well, I can drop the parentheses, put our like terms next to each other. 1 plus 2 is 3. 3i plus I is 4i. We get 3 plus 4i. We get the exact same thing. Questions on this here? Subtracting two vectors. So we'll go on and plot 4 plus 2i first. Over 4, up 2. Okay. Sure. There's our first vector. Second vector, 3, negative I. We're down here. And having this, Smartboard does make this a little bit nicer. There we go. Now we have these two here. All right, oh yeah. Not what I wanted. Maybe it's the other way. Infinite cloner. So all that does, that infinite cloner, just means I can keep grabbing them and copying them as many times as I want. Now, when we added these two together, okay, apparently it's just not. I recognize that. We went tail to point. This would be adding. Now for subtracting, we go point to point. To get this here. And then for the other one, we would go tail to point to get it back the other way. Or really, to get this, let's see here, I need to flip it up, down, and flip it left, right. Really, we end up getting here. And then he's got to be flipped. Yeah. It's a little funny how this works. Yeah. Okay, yeah, that is right. Not flip. Flip. That's right. because in the end, our new vector is going to be going there between the two. But really what we have is the negative version of this vector is the opposite. It's flipping it. And at this point here, we're at the point 1, 3, or 1 plus 3i. And that seems a little weird, and we can see it mathematically. 4 plus 2i, we would distribute the negative, making it negative 3 plus I. Our 4 minus 3 is 1. 2i plus I is positive 3i, giving us 1 plus 3i. So when we do it on a graph, point to point, tail to tail, and we end up getting this here. Now to get the other two, the reason I had to flip it is because we're looking at the negative case of it, the opposite case. But really we only had to do the first one, where we move the 3 minus I point to point, and we have our vector. Find the distance between two complex numbers. Well, I'm going to add the complex plane in. We don't necessarily need it. And it's 2 plus 3i. It's going to be over here because it's the point 2, 3 in the complex plane. 5 negative 2i. 5. Because it's really just the point 5 negative 2. Well, now we're just looking at the distance between 2 points. And the distance between any 2 points is the square root of x sub 2 minus x of 1 squared plus y sub 2 minus y sub 1 squared, just our distance formula. And for us here, the two x values are the real numbers. So we'd say 2 minus 5 squared. And our y values, in this case, are the complex terms. Or if we wanted to, instead of using x and y, we could just say that it's a and b. And at this point here, we just have to calculate this here. Now we could do this in a calculator and let it do it for us. 2 minus 5 is negative 3 squared. 3 minus negative 2, the negative and negative make a plus, giving us 5 squared. 3 squared is 9. 5 squared is 25. 9 plus 25 is 34. And that's as simplified as it gets. Square root of 34, we can use the 30xs to check. And it's 34. So the distance between these two complex numbers is the square root of 34. Questions on this here? Find the midpoint between two complex numbers. Well, I don't think we need to find another distance because it's just the distance formula. Now the midpoint, just as we thought of with the distance, well, our normal midpoint formula is x1 plus x2 over 2 and y1 plus y2 over 2. Well, given that it worked with distance, the same thing is true with midpoint, because we can just say that it's a1 plus a2 over 2 and b1 plus b2 over 2. And the a values in this case are 4 and 2. So we can say 4 plus 2 over 2. Our b values in this case are negative 3 plus 2. Now we don't have to do this step by step because we could do 4 plus 2 divided by 2 in the calculator and it'd give us an answer. Well, our 4 plus 2 is 6. Negative 3 plus 2 is negative 1. So we get got 2. Because 6 divided by 2 is 3, comma, -1/2. And that is it. Questions on midpoint? Done.